In this video, we're going to look at some simple derivations for the area of a triangle and the sine and cosine rules. So to start with, let's look at the area of a triangle, and I'm going to define some labels and parameters. So let's draw this. Let's say we have this is C, so that's A, so that's B. And so we want to get the area of this triangle. Well, we can clearly see that the area of this triangle is half of some rectangle if I construct it in this way. So let me divide it here where that perpendicular line is. So I'll draw this dashed line around here and then this dashed line around here. So clearly the area of the triangle equals half of rectangle. And then the area of this rectangle is just the perpendicular height, which would be A times sine of C. And then B is the base. So the area would be half times the area of the rectangle, which is A sine C, this height, times B. Just to clarify, the height is A sine C because the definition of the sine function, so by definition, sine theta is opposite over hypotenuse. I'll put 3 lines here. And so if we have, this is A, this is C, and then this is the height H, then the opposite, which in this case is H, it seems a bit confusing in terms of notation, but this is H over the side that I've labeled A is equal to sine C. So H equals A sine C. So if you look at this, we can see that the area of a triangle is half times the perpendicular height A sine C times the base B. And that's how we can get this area. So now we'll move on to the sine rule, and we'll see how this naturally flows from this area rule. So if we define a triangle as so it's A, B, C, I'll call this C, B, and A. Well, clearly we need to relate the angles and sines of the angles and the lengths of each side. As you know, the sine rule is that sine A over A equals sine B over B equals sine C over C. And we can see that the area of the triangle can be a useful way to get this because it involves the sine of each angle and it involves some lengths. It's not immediately obvious that this is the case, but we'll see how this pans out. So let's say we wanted to get the area of the triangle, and let's say we use the standard rule half A, B, sine C. But me using this is quite arbitrary because I've just labeled this side A and this side B. So if I just looked at a different side of the triangle and then used those sides and then the angle between them, then we could get the area of the triangle as, for example, half BC sine A, which is also equal to half AC sine B. All of these should give the area of this triangle because it's just the angle between two sides multiplied by the two sides times a half. So if we relate these, let's say the first and second equation, we can cancel out a half B. So we get that A sine C equals C sine A. And then from the second and third equation, if we cancel out a half C, we get that B sine A equals A sine B. Then if we relate these, we get sine A over A equals sine C over C. And then here we get sine A over A sine b over b. So clearly these must all be the same because sine a over a is equal to sine c over c, and sine a over a is equal to sine b over b. So we get the sine rule. And that's just a simple way of deriving it from the area of a triangle. So we needed to know the area of a triangle formula in order to get to this derivation. Now let's move on to the cosine rule. So again, we'll need to think, how can we prove something that looks like this? So in terms of difficulty, it looks slightly more difficult. So we'll need to define some parameters. So we'll have B, C, and then we usually call this side A, and this will be capital A for the angle. So the cosine rule, if you remember, is a squared is b squared plus c squared minus 2bc cosine of a. So we're trying to prove this. I need to think, how could we show this? Well, the fact it's got a squareds, b squareds, and c squareds, that should indicate that the Pythagorean theorem might be useful here, because that's a way that we could get some relationships between certain terms. Now let's think how we could employ the Pythagorean theorem into this. So we want to relate a squared to all these terms. Well, what I'm going to do is I'm going to redraw this triangle in a slightly more instructive way. So let's say we have this is B, this is A, and then I'm going to write this as X, and then this is C minus X, and then this is A, and this is a perpendicular height H. So we can find a relationship here using Pythagoras by relating something that we know is true in both equations. So whenever we're looking for an identity, we have to think there's one way of getting something and there's another way of getting something, and then relating the two. That's a simple way to look at it. So we could say here that h squared, the perpendicular height, is b squared minus x squared. But it's also the same as a squared minus c minus x squared. I'll just draw the 90-degree angle here to emphasize that this is the perpendicular height. So if we were to now expand this, we'd get b squared minus x squared equals a squared minus c squared minus 2cx, that becomes plus 2cx, minus a plus x squared, so that's minus x squared. We can cancel out x squared from both sides, and so we get a squared is b squared plus c squared minus 2cx. Now we just need to find out what x is. Well, we know x over b, that hypotenuse, equals cosine of a. So x equals b cosine of a. Putting this in, we get that a squared is b squared plus c squared minus 2bc cosine a. And now we have the cosine rule. So we've got the area of a triangle, the sine rule, and the cosine rule. And we can see how these all come together using the Pythagorean theorem and properties of areas and equating them. So hopefully this all made sense, but if you have any questions, do let me know in the comments.